So if you recall what we were doing in the last class, like we were looking at the concept of transfer function where let's say if I have a linear ODE with constant coefficient, like that corresponds to a linear time invariant causal SISO system, right, that we are studying. We could apply the Laplace transform, take all initial conditions as 0, and then one could get the ratio of the Laplace of the output to the Laplace of the input, right? So once we do that, like the quantity that we get was what is called as a transfer function of the system, right? So and we define what are called as poles and zeros of the transfer function, and I left you with 3 exercise problems, right? So I'm going to discuss the solution to those exercises problems today, and then like we would make a few observations, right? Okay. So let's take the first problem, right? So this is the system, like whose governing equation is given by y double dot t plus 5y dot t plus 6y equals u of t, right? So as we could observe, like this is a second order system, correct? So if we take the Laplace transform on both sides, what do we get? The Laplace transform of y double dot becomes s squared y of s minus s times y0 minus y dot 0 plus the Laplace transform of y dot is going to be s times y of s minus y0, right? So plus 6 times y of s, and that's going to be equal to u of s. Okay, so that's what we are going to have, right? So we collect terms, and then like we could observe that we will get s squared plus 5s plus 6 y of s. That's going to be equal to, let me do it carefully, like so we are going to get y0 plus 5s plus y dot 0, right? Correct? So I think that's due to the initial conditions, right? Then what will we have? We will have u of s. I hope this is correct. So yeah, we are going to get no, I think y0 plus 5y0, right? Yeah, that's what I missed, right? So 5y0 times s. No. I think I am doing something wrong here, right? Oh, no. Sorry, let me erase the entire thing. So if you look at the s term, I am going to get y0 sy0, right? That's about it, correct? So as far as the initial conditions are concerned, so I will write y0 times s, and then the constant terms will be 5y0 plus y dot 0. Am I right? Is that correct? That's what we are going to get, right, on the right hand side. Okay, so this will be the initial condition and this will be the input term. So as a result, y of s is going to be equal to y0s plus 5y0 plus y dot 0, the entire thing divided by s squared plus 5s plus 6 plus 1 divided by s squared plus 5s plus 6 times u of s, correct? Yeah. Now we take all initial conditions to be 0, but of course once again I wanted to do a similar exercise like what we did last class to convey that the output term has 2 components, right? So this first component is due to the initial conditions, right? So y0 and y dot 0, and that is what we call as we will revisit these terms once again, like that's what we call as the free response, right? So that is the response of the system due to non-zero initial conditions, right? And the second part is due to the input, the output of the system due to the input. Okay, that's what is called as a forced response of the system. Okay, so these are 2 components, right, of the input. Okay, so now when we want to get the transfer function, what to say, take let us consider all the initial conditions, all right, as 0. That is, in this particular problem, we take y0 equals 0 and y dot 0 is equal to 0. Okay, so that's what we have, right, in this particular condition, right, in this particular problem. So once I have that, like what is going to happen? The first term is going to vanish. So y of s is going to be just 1 by s squared plus 5s plus 6 times u of s. So if I cross multiply, what am I going to get? Y of s divided by u of s is going to be equal to 1 divided by s squared plus 5s plus 6. Okay, so this is going to be the plant transfer function or the system transfer function P of s, right, for this particular system. Okay, so please note that like I'm doing all the steps once again, so that like we recap, but from here onwards, like we would understand that you would be able to follow these steps, right. So if I give a system model, we directly take the, if you want to calculate the transfer function, like I would skip some steps, right, and we'll directly go to the answer, so that like I'm sure you would pick up what are the intermediate steps that are involved, right. So this is the plant transfer function. So immediately we see that the value of n and m are, what did we learn as n and m? N was the order of the denominator polynomial of the transfer function, right. So what is n here? 2, right. What about m? 0, right. So you see that n is greater than m, so we have a strictly proper transfer function. Okay, and what can we say about the poles of the transfer function? How do we get the poles? We solve the denominator polynomial equals 0, right. So if I solve what to say, s squared plus 5s plus 6 equals 0, what do I get? The poles are minus 2 and minus 3, right. And what about the zeros here? There are none for this problem, right. So the numerator polynomial is just 1, right, it's a constant term. So there are no zeros as far as this particular problem is concerned. And typically what we do is that we plot what is called as an S-plane. Okay, so the complex plane with the real and the imaginary axis. I think this thing could be better drawn. So let me draw it again. Okay, this is the real axis, imaginary axis, and the origin. By and large, what happens is that the poles are denoted by an cross x sign. Okay, right. So in the complex plane. Okay, so if I want to locate minus 2 and minus 3, I can locate them on the negative real axis, right, on the complex plane. Okay, so this S-plane or the complex plane is used to essentially indicate, the locations of the poles and zeros of the transfer function, right. So we see that the poles in this particular problem are going to be at minus 2 and minus 3. Okay, so once again, poles are denoted graphically by an X sign, okay, in the complex plane. The zeros are typically, graphically denoted by a small circle, okay, like an O, right, in the complex plane. Okay, that's the graphical representation. In this problem, since we do not have a zero, no, I'm not drawing anything there, right. Please don't confuse the origin with a 0, okay, that is 0, right. So this is like a small circle, right, that we draw. Okay, now some more terms. This imaginary axis divides the complex plane into two halves, right. What is called as the left half plane. Okay, so the entire plane is divided into two halves. Okay, the imaginary axis divides into two halves. Okay, whatever is to the left is what is called as a left half complex plane, abbreviated as LHP, and whatever is to the right is what is called as a right half plane. Okay, this is abbreviated as RHP. Okay, so that's the left LHP and the RHP. Okay, as far as the complex plane is concerned. Okay. Now, if you look at the what to say, transfer function of the system. Okay, so the order of the transfer function is 2 because the denominator polynomial is of order 2, and one could see that the order of the system is also 2, right? So that's something which we have already looked at, right? The order of the denominator polynomial is going to be the same as the order of the system. Okay, now we will calculate the unit step response of the system. Okay, so let's go ahead and look at the unit step response. Okay, so if I want to figure out the unit step response, like I just need to first find y of s, that's going to be p of s times u of s. Since we already know the transfer function, we just plug it in. Okay, and unit step response means what is u of s? U of s is? U of t is 1, right? What about u of s? 1 by s. If you take the Laplace transform of 1, you will get 1 by s, right? So you are going to get 1 by s, right? So this I can rewrite this as 1 by s times s plus 2 times s plus 3. This could be rewritten as a by s plus b by s plus 2 plus c by s plus 3. Okay, so as a partial fraction expansion, a, b, c are what are called the residues, right? So once again, let me write down the technique for calculating a, b, c one more time. Okay, from here onwards we will directly process them. So if I want to calculate a, what should I do? I multiply both sides by s, right? The factor which is in the denominator for that particular residue, right? So if I do that, what's going to happen? I'm going to get 1 divided by s plus 2 times s plus 3. That's going to be a plus bs divided by s plus 2 plus cs divided by s plus 3, and here I substitute the root of the denominator polynomial, right, corresponding to that residue. The denominator polynomial was just s, the root is 0, right? So if I substitute s equals 0, I just get 1 by 6 equals a, correct? So the value of a is 1 by 6. So similarly, if I want to figure out the residue b, I multiply by s plus 2. So what do I get? I get 1 by s times s plus 3. That's going to be equal to a s plus 2 divided by s plus b plus c times s plus 2 divided by s plus 3. Right? That's what is going to happen. Okay. And here I substitute the root of s plus 2, and that's going to be s equals minus 2. So what are we going to have? Minus 2 and plus 1. That's going to be minus 1 by 2. Okay. So that's going to be b. Okay. Yeah. And if I want to figure out c, I multiply both sides by s plus 3. So we are going to have 1 divided by s times s plus 2. That's going to be equal to a times s plus 3 by s plus b times s plus 3 divided by s plus 2 plus c. So once again we substitute s equals minus 3, which is the root of s plus 3, right? So what do we get? We get 1 by 3. Am I correct? Yeah, for c. So what we have is the following. So consequently, y of s is going to be equal to 1 by 6s minus 1 by 2 s plus 2 plus 1 by 3 s plus 3. So this implies that if you take the inverse Laplace transform, y of t is going to be equal to 1 by 6 minus 1 by 2 e power minus 2t plus 1 by 3 e power minus 3t. Okay, that's what we are going to have, right? Okay, so this is the expression for y of t. Okay, the step response. Okay, so this is the step response of the system, or to be more accurate, I should call as the unit step response. Of course, if I suppose, let's say instead of giving u of t equals 1, let's say I give u of t equals 5, how will this output change? I just multiply by 5. Why? We use that property of linearity, right? So if I give u of t and I get y of t, if I give c times u of t, the output should be c times y of t, right? I use the property of what is called as homogeneity, right? So as far as a linear mapping is concerned, right? So essentially we scale it. That's it. Okay. So that's the unit step response of this particular system. Okay. So what can we observe? All right. Let's write down what do we observe from this unit step response. Right. Okay. So what are the observations? What can you infer from by looking at this expression? I'm sorry? Okay, very good. Okay, let me write down whatever you are summarizing. Okay, as let's say t tends to infinity, y of t tends to 1 by 6. Right, that's what you want to convey. Right, so this is what is called as the steady state value. Okay, so the value of y of t tends to 1 by 6, right, as t tends to infinity. Okay, good. Okay, any other observation? Of course, what about the initial value of y of t? If you substitute t equals 0, it should be 0, right? Because anyway, we assume all the initial conditions to be 0, so you can double check your answer, right? So it should be 0, right? If it's not 0, we have a problem because we are only looking at the forced response, right? In the derivation, in one of the intermediate steps to calculate the transfer function, we took y0 to be 0, y dot 0 to be 0. Okay, so obviously y at t equals 0 should be 0. Okay, and that's something which we can immediately observe. Okay, any other observations? We discussed this, I think, maybe in the first week or last week. We saw that the class of systems that we are considering basically are what are called as linear time invariant, single input, single output, causal dynamic systems, right? Which we are going to characterize by what are called lump parameter, spatially homogeneous, dynamic continuous time models, right? Deterministic models, which essentially take the form of linear ODEs with constant coefficients, right? So, and we saw that, if you give me a linear ordinary differential equation with constant coefficients, like we discussed that, the solution is unique and the only solution is the exponential solution, right? So you can see that the exponential function comes as a solution here, correct? What can you say about the exponents of the exponential solution? What are the exponents, of the exponential terms? Yeah. What are the exponents of the exponential terms? See, what do I mean by exponent? If I have e power minus at, right? A is the exponent, right? So, what are the exponents of the exponential terms here? Yes. So, in this particular example, they are minus 2 and minus 3. Okay. So, which happen to be the poles of the system. Okay. And in this problem, the poles happen to be real. Okay. But in general, poles and zeros, okay, let me write it as an aside, okay, here, okay, poles and zeros can be complex conjugate pairs. Okay, we could also have complex conjugate poles and zeros. Okay, why should they? Can I have complex numbers as poles and zeros? Yes, I can, but I need to also have the conjugate as a pole, right? Because since we are dealing with real polynomials, right? So because we are dealing with dynamic systems where the governing ordinary differential equation has real numbers as coefficients in the ODE. So consequently, when you take the Laplace transform, you will get a polynomial in S, but the coefficients of the polynomial are real. So once you have a real polynomial, that is a polynomial with real coefficients, you could have a complex root, but the conjugate must also be a root. Okay? So in general, pole zeros can be real, they can also be complex, but if they happen to be complex, the conjugate must also be a pole or a zero. Okay? So that's something which is very important. So we would observe that the exponents of the exponential terms in general would be the real part of the poles. Okay? So in this particular example, -2 and -3 are essentially real numbers, right? Okay, the complex part was, or the imaginary part was 0, right? So that's why we have got the terms as e power minus 2t and e power minus 3t. Okay, so in general, the exponents of the exponential terms would be the real part of the poles. Of course, we can also say that the poles, in a certain sense, we will shortly observe that, even I can write, complex terms in terms of the complex exponentials, right? You remember the Euler's relations that we discussed? E power j omega t was cos omega t plus j sin omega t and so on, right? So we could generalize it, but for us, to be more pragmatic, I am going to just write a statement which we are going to use. Okay, in general, the real part of the poles would appear as the exponents. Please note that we are going to have since I have two poles in this example, I am going to have two exponential functions, right? Okay, so this is like a linear combination of these exponential terms. Okay, so we are going to have two exponential functions and in this particular problem, and the exponents are going to be the real parts of the poles in general. Okay, so here we have -2 and -3. Okay, so that is a second observation, right? So what else can we observe? Of course, we would prove this in general, okay, but I'm just making this observation so that we can go to problems 2 and 3, okay, and then correlate with some other important concept, right? So what about Bibo stability here? See what we learnt as bounded input, bounded output stability, right? So that is what is bounded input, bounded output stability? My output should be bounded for all possible bounded inputs, right? For all time, correct? So is a step a bounded input? You would agree that the step is a bounded input, right? Is the corresponding y of t that we have calculated, is it bounded? Okay, so do you think the magnitude of y of t is bounded here? Okay, so do you think it's stable in that sense? Well, the answer is it is, but then please note that it should be bounded for all possible bounded inputs. We are testing from only one case, for only one case, and it so happens that it is Bibo stable. That's a generalization which I want to make here, but we'll prove it more carefully, okay, later on when we look at stability, right? So we observe that the magnitude of the output y of t is bounded for all time. Okay, so that's an observation we can make, right, from this. And it so happens that this is also bounded input, bounded output stable, the system, right? We would come to that interpretation by the end of this class. Okay, yeah. Okay, is it clear how we got this expression, and then how we simplified and observed certain characteristics of this response? Okay.